Let's now do a mathematical problem to solve this, an example problem. Okay. Oh, actually, before we do that, let me say one more thing. If you're trying to measure angular size, there is a rule of thumb that's pretty cool, actually the rule of the finger. If you take your index finger and you can cover it, like just covering the moon, then that is considered a 1 degree angle. If you take a closed fist, average person now, it's 10 degrees, and if you take an open hand and it can obscure it with your open hand, it's 20 degrees. So you can kind of get a rough estimate of how big something is using this angular size rule of thumb. Now let's do an example. The moon's angular diameter is 1/2 degree. Its distance is this right here, 384,000 kilometers. How big's the moon? Now what's our equation? Well, let's go back. That's that L thing, right? L equals 2 pi dA. So we have L is equal to 2 pi dA over 360, right? So if I take my write this down. I'll say 2. Now pi, if you recall, is 3.14. If you don't know that, you do. Now d is the distance, so that's 384,000 divided by, and the angle is 1/2, right? Actually, for 1/2, let's say 0.5, and the other number at the bottom is 360. So now I want to take my calculator. So I have my calculator right here. So I'm going to take 2 times 3.14 times 384,000 times 0.5 divided by 360. And the answer is 3,349. So the answer is, hold on, let me get the pen back. The answer is 3,300 and let's just say 50 kilometers. And you know how big the diameter of the moon is? 3,350 kilometers. So you can actually do this. It's just plugging into this cool little equation. You can determine what the answer is. That's pretty cool, isn't it? Very, very cool. Okay. That leads us to another discussion here, something called parallax. Actually, let me do this there. Now, if you look at this sort of video clip that we're watching right now, this is the idea of parallax. Now, when you look at the objects, which one is moving faster, the ones in the front or the ones in the back? Now, it appears that the ones in the front are moving faster, but these objects in the back are the same size, and then the ones in the front appear, first of all, to be a lot bigger, and that's because they're closer to the person who's watching this. It's like on a video, like cart going back and forth. But they really are moving the same speed. So that's kind of the concept of parallax. But parallax helps us to determine some interesting things. So what parallax can help us do is that if I have the Earth, now this is the Earth's motion around the sun. Actually, these classical astronomers did not buy into this because they still thought that the Earth was the center of the solar system. But they understood the concept of parallax. So if I take the Earth here on one particular day, today is, let's just say on January 1, Jan 1, and then you go 6 months later and go June 1, the Earth is now a distance completely opposite on its axis down here, right? Well, if they then measure this angle right here, they call it the parallax angle right here, they can determine how far a star is away, this particular star. They can determine exactly how far this distance is. So the question is how far is this star away from the Earth? Well, you use the same concept. Similar to the angular size, but they measure angles, okay? So here's a way to look at it, right? If I know a distance here, x to y. Now, in the Earth-Moon system, we know the diameter of the Earth's orbit. So if you know that, that's basically kind of how you do this. But I could just measure this distance with a GPS if I was outside or something like that. And then what I can do is I can measure this angle here with like a protractor. This is somebody's eye, and we know this is 90 degrees. We can find out what this angle is right here. And then you can determine how far that thing is away. You use another equation that's kind of cool. You'll take b, B is the distance between the two objects times 360 over 2 pi. And this funny little symbol, all right, that little symbol is called theta. It's just an angle symbol that scientists use. It's actually Greek because it came from the Greeks. All right, so let's see if we can do a mathematical thing. Get your calculators out. Two measurements were made of a mountain some distance away. The distance between both measurements was determined to be 1.5 miles, and the angle was 1.25 degrees. How far is the mountain? Now, what's that equation again? All right, R equals, all right, let me write that down. R equals, now I can't got it in my head here. It's, where did I put it? B 360 over 2 pi theta. B times 360 over 2 pi times theta. Now, what was B? Now, what was B in this case? That's the distance. It's 1.5 miles. So 1.5 times 360 over 2 times 3.14 times, now what was our angle? I forget. Half a degree? 1.25 degrees. 1.25 degrees. We then get our calculator out. Now I've got things on the top and the bottom, so I'm going to say 1.5, I'm going to use the parentheses there, times 360, parentheses, divided by, parentheses, 2 times 3.14 times 1.25, close parentheses, that this building would be 68, boy, did I pick a, oh, what did I do there? All right, my example is not a very good example because what I'm getting here, my building, actually this is a mountain. That would still be too high. I get 69 miles tall because my unit here was 1.5 miles. So if something is 69 miles tall, Mount Everest I think is like 6 miles tall. So yeah, this would be not a very acceptable problem. But that's the idea. You would do the math the same way. I should have probably thought through my mathematics. Okay, that's how you do this. Now, let's actually close this out. Let's change gears a little bit. The motion of planets, so you should copy this down. The big problems with the classical astronomers, they were trying to figure out what's up with the planets. Now, we talked in the last podcast about the retrograde motion. They were trying forever to try and figure out what is the arrangement of the planets and the stars and everything, and the planets screwed them up because of that retrograde motion. So Mr. Ptolemy, this is Ptolemy over here, he came up with a solution. Now, the word solution isn't, he got it wrong, but he had a pretty good idea, though. It was pretty impressive, really. What he did is he said that the Earth, of course, was the center of the universe, followed by the Moon, Mercury, Venus, the Sun, Mars, etc. But because they sometimes went backwards, he said what they're actually doing is they're doing this thing, and he called them epicycles. Write that down. Is that basically what Venus would do is that even though it rotate around the Earth in a circle, not an ellipse as we discovered, they also would rotate around a central point. Those are called the epicycles. And so that would be true of all these things. They would have these little epicycles. Let me show you. I think I have a little video clip that shows you this. So this would be the Earth right here. And as the planet, which is the red, goes around, I'm not sure what planet that is, probably Mars or something like that, you can see what it's doing. And if you look over on the side right there, you can see what it's doing is it's shaping out the motion of its path as time goes on. Now I should probably back it up and then see if we can do that. So you can see its motion right here and see how it comes back down and then back up. So they're seeing this thing rotating around the red dot, if you will, which is the planet, probably Mars, and that's how he explained it. Turns out that even with this really, really cool classical model, it didn't really work. There were just mistakes, and he tweaked it, and it still didn't work. So it was nice, and that was what the classical astronomers essentially did. They used this is the fancily called the Ptolemaic model, and it was very cool, and it worked-ish, but it wasn't perfect. So that's what the classical astronomers, basically the Greeks, figured out. Some of the stuff was great. They did a lot of really cool math stuff. But their final model, which is the one we're looking at, or actually I should back up, this final model turned out to not be correct. And but hey, we learned something, and then that model, in fact, it lasted until about 1500 when we move into what's called the Renaissance. Okay. All right, so that's the end of classical astronomy.